In astrophysics, black bodies are not just important to study and understand stars, but actually they are quite crucial to understand our universe as a whole. The story behind this started in the 60s, where these two guys were puzzled and looking at this detector. This detector was basically pointing up and kind of surveying the sky, and their prime goal was actually to try to find whether Russians were detonating nuclear bombs in space. It was quite an important endeavor in the Cold War because Americans were afraid that maybe Russians had more capabilities than they thought. And one of the reasons why they were very puzzled and worried is because by observing with this thing, they actually discovered this result. They found out that there was a signal, actually quite powerful, but that was coming apparently from all directions. And this was very worrying because it could mean that Russians were not only detonating nuclear bombs in space, but they were actually doing it almost everywhere. Of course, if you were to work out how much energy you would need for this emission to be coming from nuclear bombs, you'd realize that that material would not exist on Earth. So that hypothesis was slowly excluded. And they actually decided to inspect this antenna and realized that inside it, there were a lot of pigeons living and doing what pigeons do. It was incredibly dirty. And obviously, when you discover pigeons living in your antenna, you think that your signal is probably to do with whatever pigeons were doing. But interestingly, after actually cleaning the entire detector, making sure that pigeons weren't there anymore, the signal was still there. And it even led to these two guys getting a Nobel Prize for the discovery of the cosmic microwave background. So Arno Penzias and Robert Wilson, that you can see pictured here, were the guys that essentially discovered it. Here they are standing in front of the instrument after they got the pigeons to leave, and they were sure that they were actually detecting the cosmic microwave background. So this was not coming from nuclear bombs or pigeons. And I think one of the most interesting things is that it's radiation. It's one of the oldest radiations that we can see and detect here on Earth that was emitted essentially when the very first hydrogen atoms formed, only a few 100,000 years after the Big Bang. And even though when Arno and Robert looked up, they could see something that was very homogeneous, right now we actually see that there are some small differences across the sky. I mean, these differences are incredibly small, so they're on these scales, very, very small, but they are important and significant. So currently, this is how the CMB looks like. It is almost a perfect black body emission with a temperature of 2.7. Of course, this is the cosmic microwave background today, essentially almost 13.7 billion years after it was first emitted. And because the universe is expanding, as we'll see, this radiation has been redshifted all the way from sort of the infrared into the microwave. Currently, because of the temperature of the CMB, the peak using just Wien's law is at around 1 millimeter. So the wavelength of these photons is 1 millimeter. But if you actually go back in time, this radiation was emitted actually at a redshift, and we'll discuss this more, but at the redshift of about 1,100 actually implies that when the radiation was emitted, the peak of the black body emission back then was more around 964 nanometers. And this would mean that because apart from the peak, there's still some extension into the blue. If there were any humans, back then, obviously there weren't because nothing existed. This was the moment where the first atoms, actually hydrogen atoms, formed. But if we were around there, we would be able to see some of this cosmic microwave background actually with our own eyes because it would extend into the red and it would look quite red. Another thing that is worth pointing out, we will not be discussing this a lot, but when you move to the longest wavelengths, we could still think that we're looking at black body emission, but in practice, whenever we detect something, actually, it is not coming from thermal radiation. That is because when you go to the longest wavelengths, the emission is really, really weak. It's very hard to detect black body emission at the longest wavelengths in the radio, even if you're looking at something that is very, very cold. But typically in images like this, when you see radio, and this is an interesting cluster of galaxies that is called the sausage cluster. For some reason, Germans discovered it. And when you see also X-rays, The big difference is typically X-rays will be coming from thermal, sort of not really black body radiation, but from very high temperatures that correspond to the peak in the X-rays. This radio emission is actually not thermal. And typically when we detect things in the radio, we're almost certainly looking at synchrotron radiation, specifically at these very large scales.